Thank you, and I would like to thank the organizers for inviting me to this very interesting conference. So I'm going to talk about something quite different from the previous talk. So I'm interested in generalizations of classical relativity theorems, such as singularity theorem and the area theorem that I'm going to talk about today, but in the context of semiclassical gravity. So I'm particularly interested in quantum fields on a classical curves background. A large part of this talk, though, it's going to be pretty classical. So this is based on 3 papers. The 2 were published a couple of years ago, and the third one actually appeared on Archive this morning, so check it out. So let's start with some motivation. So the classical relativity theorems, I don't think I need to convince this audience. They have powerful predictions for what happens in our universe with general assumptions. So their main thing is that they don't specify what kind of metric we have. A lot of times there's no symmetry. We have some very general assumption about the space-time, and then we have predictions on that. These assumptions, and in particular the energy conditions, which I'm interested in, are violated in the semi-classical regime. So in the regime where quantum effects become important, we can now directly apply those classical relativity theorems. So what I'm interested in is which of those theorems still hold in the semi-classical regime. What are the new assumptions for that? Or maybe we also need to modify the results of this theorem. Maybe the predictions of this theorem are different when we have quantum fields. So this is my motivation. So as I said, I'm going to talk about two theorems in this talk. One is the Penrose singularity theorems. In general, the singularity theorems predict the existence of singularities. In the context of GR, a singularity is when we have at least one incomplete and inextendable causal geodesic. So this is the definition I'm still going to use in the semi-classical regime. So in quantum gravity, if you've been to quantum gravity talks that discuss singularities, they always want to resolve singularities. They don't think that a full theory of quantum gravity should have singularities. It's considered a problem of the theorem. But I want to go one step back and ask the question, what happens to semi-classical gravity? Are singularities predicted in that context, or we can have a singularity resolution in that regime? The second theorem is the Hawking area theorem, which is that the area of the black hole horizon cannot decrease over time. But the situation is slightly different here because we really know that in the semi-classical regime, the Hawking area theorem has to be violated. And the reason is the existence of the Hawking radiation, which is probably the most famous situation of that semi-classical gravity has been really successful. This is really a regime where we have quantum fields, we have a classical background, we have something different from what the GR predicts, is that the black holes radiate, they have radiation, and so their mass, if you just left a black hole on its own, we have a Hawking radiation, its mass decreases over time, its area, the area of the horizon decreases over time. So definitely in that regime, we don't expect the Hawking area theorem to hold. So the questions I want to ask here is if the area theorem is always violated semi-classically, or there's some quantum fields that violate it and some don't. And the second question is if there's a weaker version of the theorem that could be obeyed by quantum fields. So let's go to the more technical part. So I'm going to prove these theorems directly using the formation of the focal points. So I'm only going to talk about null geodesics in this talk. Of course, there's a version of the singularity theorem, the Hawking type singularity theorem, that's time-like geodesics. But I also have some papers on that, but I'm not going to discuss it in this talk. So we have a codimension to space-like submanifold. We have a causal geodesic normal to P, and then a focal point is the point where the non-zero Jacobi field vanishes. Usually I have a bit of more physicist-directed definitions here, but I don't think I need it for this audience. But the important thing for the singularity theorem and the area theorem also is after a focal point, we have no extremization of length of a geodesic. As I said, I'm going to only talk about null geodesics. So instead of the length of the geodesic, for null geodesics, we have the energy or action integral. So when we're talking about focal points instead of conjugate points, for example, we always need the surface, which is this codimension 2 space like submanifold P. That's where our geodesics are starting. They're normal to the P. These are all the geodesics that I'm going to consider, null geodesics. And we want to see if there's a focal point, let's say before some point Q of the geodesic. So here the integral is, let's say, from 0 to some affine parameter L. So what we do is we do a variation of this action integral. So U is the tangent vector to the null geodesic, and V is a variation vector which is a transverse to the tangent vector. So we create a variation, we create a family of null geodesics that is a gamma S, and then we take the derivative of the action integral in terms of that direction, and then we take S to 0. So the first derivative of that, ds at S equals 0 is 0, exactly because we have null geodesics. So what we take to consider the formation of a focal point is the Hessian, which is the second derivative of that action integral. And after quite a bit of calculations, we end up with this expression. So these are the derivatives of the variation field. The Riemann tensor appears, and it's contracted with two of the variation vectors, two of the tangent vectors. And this term here is about our hypersurface P. So it's a boundary term, and this is the shape tensor or the second fundamental form. So it contains information about the surface. Yes? They're geodesics that are kind of parallel to each other, right? It's a family of geodesics. But we're only interested in the S equals 0 geodesic. No, it's not 0. So the one we're interested in to be null is the S equals 0. That's the one. So this is a quantity we will consider. So the second step is to define this variation field. So what we do is we take the tangent space on P and take the orthonormal basis on P. This is a codimension 2, so we have from 1 to n minus 2. N is the number of space-time dimensions, and then we parallel transport them around the geodesic gamma. And then we take f as a smooth function, where with the boundary condition f of 0 equals 1 and f of L equals 0, and then sum over all these vectors I. So this is an appropriate vector V, right? So this is what we're replacing V with. We're replacing the EIF, and then we sum over that. And that simplifies the expression, and it makes an expression in terms of f. So the first term only depends on f. The second term is the Ricci tensor contracted with two null vectors, and the boundary term now can be expressed in the mean normal curvature vector field of our submanifold. And we have the condition for the existence of focal points. So the condition we're interested in is the focal point before some point Q. Then the Hessian of V has to be less than 0 for some variation vector V, and in particular we're gonna look at this one. So this is the condition for existence. So this expression is the expression we're going to check whether or not we have the formation of a focal point. So if this expression is less than 0, then we have the formation of a focal point. And this is in the heart of the proof of both theorems. So let's see the classical theorems. First, the Penrose singularity theorems. So we have three conditions are in most singularity theorems. We have the causality condition. The M is globally hyperbolic. It admits no compact causative surfaces. And we have P, the compact technol smooth space-like submanifold, codimension 2. So this is our hypersurface where we're starting the geodesics. The second is the condition that I'm most interested in, which is the energy condition, or it's really a condition on the curvature. And this is really the null convergence condition, although some people are calling it the null energy condition. The null convergence condition is a condition on the Ricci tensor, while the null energy condition is when you use the Einstein equation and you express the same thing in terms of the stress energy tensor. The third one is the initial condition, and for the mean normal curvature vector field, we have that H is less than 0. So this is usually called a trapped surface. Right, so we need to have a trapped surface, so a hypersurface where both null normals have negative expansion in order to consider. Yes? Only if you use the Einstein equations. Otherwise, I don't know how to have the stress tensor there. They amount the same thing in terms of, they have exactly the same form, right? Because it's null. So it's just T mu nu, U mu U nu in the terms of the energy condition. But this is for all space-time. This condition here is for every space-time point, right? I mean, for the stress energy tensor, you can consider you have some kind of matter, and then you have to see if it obeys that. And then if you apply Einstein's equation, then you can apply that to the Ricci tensor, right? I mean, yeah, I mean, I don't see how else you would get it without the Einstein equations. And then the result is that gamma is incomplete, and in fact it has length less than L, which is equal to 1 over H. And you might worry about the affine parameter, because in null geodesics we can do an affine reparametrization, but we actually fix the affine parameter by this arbitrary condition. We just want to fix it. We require that oh, I have a mistake here. This should be down. And this is the mean normal curvature vector field on P and its inner product with a tangent vector of the geodesic. We fix it to 1, so we know how much the affine length is, and we can do a reparametrization. So this is the Penrose singularity theorem. It's actually pretty easy to prove it when you have the focal point condition. So we have the null convergence condition, which means that this term is always positive, non-negative. The second is we have to choose a function. So we're free to pick a function as long as it has the right boundary conditions. So in this case, we just pick a very simple linear function, and then we can compute exactly the first term. The third one is the trapped surface, so H is less than 0, so that also fixes the sign of the right-hand side, and then this inequality gives us that we have a focal point for L greater or equal than 1 over H, which is the result of, which tells us that there's a focal point before that L. Now we need to impose the causality condition, and the condition 1 implies that the p-normal geodesic have no focal points, and so their length is at most L. So that concludes the theorem, this contradiction between the energy condition and the initial condition and the causality condition. That leads to the geodesic incompleteness. So this is the Hawking area theorem, which at first looks quite different, but actually has a very, very similar proof. So the causality conditions are quite different for the Hawking area theorem. So we have the condition that M is strongly asymptotically predictable. So that means that it's asymptotically flat and also forbids the existence of naked singularities. And then if we have an strongly asymptotically predictable spacetime, we can define the black hole as the area that is not included in the spacetime's J minus of scribe class. So it's the area behind the event horizon. Of course, it's not necessary that the M has a black hole, but we assume that it has a black hole, that this area exists. And of course, this conformal diagram is only for a simple spherical symmetric case, but the area theorem is not for spherical symmetry. It's quite general. It does not assume any kind of metric. The second condition is, again, the null convergence condition everywhere on M. And then the strong asymptotic predictability assumes that there is a globally hyperbolic region. So we have sigma 1 and sigma 2 space-like Cauchy surfaces. And we assume that the sigma 2 is in the future of sigma 1. Then H is the event horizon. And we define this calligraphic H1 and H2 as the intersection between the H and the Cauchy surfaces sigma 1 and sigma 2. And then the result is that the H2 is always greater or equal than the H1. So as we progress in the future of the horizon, it always increases or remains the same. And this is kind of a pictorial representation of that. So we have the sigma 1, the sigma 2, and these dotted lines are the null generators of the horizon. And then these are the two areas we're comparing. So as I said, the proof is quite similar with the Penrose singularity theorem. So again, we have the null convergence condition. So this term is non-negative. We pick the same function. We know what this term is. But now, after that, it is slightly different, the conclusion. So if this is the tangent vector of the null generator UM, and H mu is the mean normal curvature vector of H1. So if this is less than 0 for the H1, then we have a focal point that appears before L. So this is the same conditions that comes up. But the null generators cannot have focal points. That's also from strong asymptotic predictability. So since there are no focal points, then the contradiction now leads that actually the U mu H mu has a different sign, is larger or equal to 0. And so the change of the area of the horizon, which can be expressed as the integral of this quantity, is actually non-negative. So this is the conclusion of the area theorem. So these were classical theorems. So now I'm going to start talking about new things. And the reason I discussed the proofs of that probably most of you have already seen, is because we're actually going to use a very, very similar method to prove the generalized versions. We're still going to use this focal point condition. So, what is my motivation for considering weekend energy conditions? So the thing is that all pointwise energy conditions are violated by quantum fields. There's a quite old theorem that shows that under some general quantum field theory conditions, there's always states that admit negative energy. So, of course, these theorems have conditions that are about the curvature, but if you want to connect the quantum fields with classical curvature, then the fact that they admit negative energy in the expectation values of their normalized stress tensor also means that the Ricci contracted with null vectors, for example, admits some negative values. And that means we cannot directly apply those classical theorems. So in quantum field theory, there are restrictions on this amount of negative energy that the expectation value of the stress tensor can admit. And this comes in the form of quantum energy inequalities. They have a restriction on the magnitude and duration of any negative energy densities or fluxes in the context of a quantum field theory. So this is an example of a quantum energy inequality, maybe the most famous one. It's bound on energy density in Minkowski spacetime. That shows pretty much all the features of quantum energy inequalities. So we have the stress tensor. Here it's contracted with time-like vectors. So this means that it is renormalized or normal ordered in this case in order to get rid of the singularities that appear in the two-point function and, of course, the stress tensor in quantum field theory. So this is the expectation value, and omega is a class of states. So here, and usually in quantum energy inequalities, we consider Hadamard states. These are just states that have a known singularity structure, so we're able to renormalize the stress tensor. So this is integrated over some time like geodesic, and f is a test function. So the bound that we have here is negative, and it depends only on the test function. So this is the bound that we like to see. We want it to not, in general, depend on the state. These are kind of the best type of bounds because they're very general. So this is a finite bound if f has a compact support. And what is the interpretation of this kind of inequality? Well, if we consider that f has a small support, then that is a small segment of the time-like geodesic. So it allows for it can allow for a large negative energy because this bound goes about as 1 to the tau to the 4th. So if we have a small time, then it allows for a lot of negative energy. If we have a large time, then it does not allow for a lot of negative energy. And in fact, if we take that to infinity, this bound becomes 0. So the condition I'm going to use for this theorem is a weekend condition. It is inspired by quantum energy inequalities. In the theorems, I'm going to use the Ricci tensor contracted. We can think about it's contracted with time-like or null vectors. Here I'm going to talk about null, as we're going to see. And the bound is a general bound. So inspired by this expression, which is the L2 norm of the second derivative of f, we consider a bound that depends on the L2 norm of f and m derivatives on f and the L2 norm of that. So this bound is a bound like that, where m is equal to 2 and q0 is 0. Yes? Yeah, exactly. I mean, you can pick a bad function and then it's minus infinity, it's always obeyed, but it's just a bad function, right? So we have freedom to pick a good function here. So if we pick a function with compact support, then it's finite, and that's what we usually pick. Oh, it doesn't. It's a time-like geodesic, and it's a tangent of that time-like geodesic. So it does not depend. The bound, the right-hand side, does not depend on you. Yeah. So the right-hand side. Yeah. This is about. If you take the average to 0, to infinity. Sorry. Oh, this is just about, so this is a time-like vector contracted with a stress tensor, right? So this is basically the time-like vector here just telling you that you take the energy density, basically. Oh, you're worried about the length of the time-like vector. Yeah, you can take it as a unit vector, sure. So the way we calculate that is we have the stress tensor, right, of some field, and then we contract it with null or time-like vectors, and we have a quantity. So no, the right-hand side only depends on the function you pick. It does not depend on that. Mm-hmm. Oh, are you worried about the renormalization of the vector? This is true for all time like u, yeah. So, okay, this is time like. So this is just an example, right? Yes. So for null vectors, there's actually a problem, which I'm going to discuss. Right? This is only time like. Yes. Yeah. This. So this is only the mth derivative, is not up to. You can actually group the constants, right? So if you have if you have m-1 derivatives, you can find an inequality that you can actually write it as a linear combination of f of m and f. So you don't need other derivatives. Yes? No, u is the tangent to the time-like geodesic here. Yeah. So this is the Penrose singularity theorem. So here we're not going to worry so far about the quantum things. So this is a purely classical theorem with a weakened energy condition, right? So this is just an assumption that we put as the original conditions. So far we have not assumed any quantum fields here. It's just inspired by quantum inequalities. So what we have here is the condition that appears in the null convergence condition. We're just integrating it over a segment of a null geodesic, and we assume that it has this kind of bound that is inspired by QEIs. The second condition, but is part of the energy condition, is a pointwise condition. And here, what we assume is either one of the two scenarios. So the NEC is obeyed after we measure the mean normal curvature of our hypersurface, or it's violated before we measure that. So these are conditions that kind of help and I'm going to show the reason in a moment that we have to impose those conditions. So what we would like is for this L0 in either of these cases to be smaller. Remember that we fixed the parameterization of the affine parameter so we can compare. So we want it to be smaller than L. So we don't want this condition to dominate our theorem. So we want it to be some small time. Then we have the initial condition. So remember in the Penrose theorem, we had just h was less than 0. But here we have h is less than a function that depends on all the parameters of the problem. So the qm and the q0 that appear in the new energy condition. We have the L0 when we take this pointwise condition. We have the L, the time for the appearance of the focal point, and the rho 0, which is also in those conditions. So of course, we know exactly what this function is. I'm going to discuss in a moment. But for now, what we're considering is we have a weaker energy condition. It's just an average condition. We have a stronger initial condition. We need not just a trapped surface, but a more than trapped surface. And the causality condition is exactly the same. Sure, let me show you the idea of the proof of this theorem. So we have the condition for the formation of the focal points that we also had in the classical theorems, and we have the energy condition we want to use. So we can kind of immediately spot a problem here. So we have the function f in the condition for a focal point that has those boundary conditions. And then in the energy conditions, as I discussed, we want some function of compact support. So otherwise the bound would diverge, and it's not a very good bound. So this cannot be the same function. So we cannot immediately apply this condition to the condition for the formation of the focal point with the same function and just pick a function that we have. So what we do is, instead of having the function f in the energy condition, we have a function phi f. So the function phi is 0 at 0, and then it becomes 1, it's a smooth function, it becomes 1 at L0, and then it remains 1. While the function f, that we have the condition of the focal point, starts at 1, and after L0, it goes to 0 at L. So now both functions have the correct boundary conditions. So here they're null geodesics. Yes, exactly. We have fixed the length. So what we're applying the energy condition is this product phi f, which has the correct boundary conditions. And now we can pick a function, and we have a freedom to pick these functions f and phi. So, but we know everything with our average condition and the pointwise condition that we have. Remember, the pointwise condition from 0 to L0 or from minus L0 to 0 is actually quite similar from 0 to L0 and before. And we are expressing this, the quantity in terms of the rho 0. This is the pointwise condition here, and then this is the average condition here. So we know everything. It's just constant, except the functions, right? The L2 norm of the functions. So the only thing that remains is to pick the functions, and we have some freedom to pick the functions. So we've done actually two different things. The one is to just pick convenient functions for a general M, which is what we actually do in both the singularity theorem and the area theorem papers. We picked some incomplete beta functions and computed these L2 norms. Or the second option is to actually optimize this problem, but we're able to do it for m equals 1. For general, m is a bit of a tricky problem, and we want kind of a simple function too. So we optimize for m equals 1, which is a case of interest. And then after we pick the function and we compute those L2 norms, we can just calculate what is the initial mean normal curvature that we need. And we compute what mean normal curvature we need. We have this function, is relatively complicated, but we have it written out. So if we know these parameters, we can figure out how much h we need to predict a singularity. Now let's move to the area theorem. So I have two questions for the area theorem. So the first is, what is the weakest energy condition so that the classical area theorem holds? So this is, I have simplified a bit this question. So the weak energy condition to follow the original proof, right? So there might be other proofs that we can change the causality conditions. For example, you need different things. So for this kind of proof, for this, all the other conditions the same, what is the weakest energy condition? You might think it's the null energy condition, but it's not. It's actually this condition, which is an average condition. So in order to have a focal point, what we need is this quantity. This is the tangent to the null generators. This is the mean normal vector field to be less than 0 to conclude the non-decrease of the horizon, just like the original theorem. So to have that, the only thing we need is the average of this quantity to be more than this positive bound. So this is not like a quantum energy inequality bound because the right-hand side is positive. So this is not expected to be obeyed by quantum fields. Nevertheless, it is much weaker than the original null energy condition that is usually cited as a reason for the failure of the area theorem in quantum field theory. And here's an example of such a condition. This particular case was discussed by Martin Lesurde a few years ago, and this is the damped ANEC. So this had a particular function, exponential function e to the minus c lambda. And what is interesting here is if we take c equals 0, this is actually the half ANEC. So the half average null energy condition. So of course, starting from a point, we can't have the full ANEC. We don't have a full geodesic. We have to start from somewhere and go to infinity. And that is only required to be more than 0 in order to prove the classical area theorem. Again, this is not a condition obeyed by quantum fields, because the only thing that's obeyed by quantum fields is this kind of quantum inequalities that tell you about how much negative energy you can have. The ANEC is also usually obeyed by quantum fields. Is actually a very, very good condition, but the ANEC is over an entire geodesic, and it cannot be used here. So average, yeah. So the half ANEC needs to start from a point, and it's not generally obeyed, because you can imagine you put some positive energy on the other side, you put some negative energy after your 0 point, and it's violated. So what happens if we have a condition that is inspired by quantum energy inequalities, like the one I showed you for the Penrose singularity theorems? So in this case, we have a different area theorem that does not have the same conclusion. So we have our energy condition, which is the same that I discussed before. And here in our paper, we actually only had scenario 1 from 0 to L0. But here, the rho 0 can actually be negative. And in fact, in applications, we will assume that it's negative so that it allows for black hole evaporation. The causality condition is the same. And now instead of having that the change of the area of the horizon is non-negative, so the horizon can only increase, we have a bound on the evaporation rate. So the change of the area of the horizon is more than a negative quantity. That is exactly the same as the one that appears in the Penrose singularity theorem. It depends on the parameters of the problem. So instead of saying the horizon cannot decrease, the horizon can decrease, but it can't decrease very fast. And the reason that it cannot decrease very fast is, of course, the bound on the negative energy. So this is a generalization of the Hawking area theorem, that instead of predicting the horizon only increasing, it predicts a bound on the evaporation rate. So it allows for black hole evaporation. Of course, this does not mean that if we have a field that obeys a condition like that, the black hole necessarily evaporates, right? It just allows for evaporation. It's not a mechanism of evaporation. So in the last part of my talk, I'm going to talk about an application, which is a bit of a toy model. I'm going to explain the issues here. So first of all, let's discuss the quantum energy inequalities over null geodesics. Sorry, change the notation here. I'm not sure why. These are null vectors here. So the question is, can we prove a quantum energy inequality that is of the form I showed you before? Here I put one derivative on f, so that is the equation is scale invariant. But is here the right-hand side can be finite for the class of states we're considering? So this is the question, can we prove that condition? It turns out we can't, because there's a counterexample. So in order to prove that condition, we need to prove that it holds for all states that we're considering in quantum field theory, but we only need one state to violate that in order to say that it doesn't hold. And those states were discussed by Fuster and Roman about 20 years ago now, where they considered the following state. It's a relatively simple state. It's a sequence of vacuum positive particle states. And what happened is they allow the momenta of the states to be unbounded, as large as we want. And as the momenta grew more and more, became more parallel, to the special part of the null vector, and then the right-hand side diverged. So it was minus infinity. So there was no finite bound in this explicit example. So if there is no finite bound in this explicit example, we cannot state an expression like that without further assumptions. So this presented a problem for a long time in order to have quantum energy inequalities over null segments. So the simplest probably idea is to introduce a cutoff. So since the problem is the three momenta of the state, we can put a cutoff on the three momenta of the state and restrict that three momenta. And then we can write that the G Newton is less or equal than this UV cutoff, which is now, we can translate the momentum cutoff to a length scale cutoff. And this is the UV cutoff over the number of fields that we have here. So to understand this inequality, if the UV cutoff is exactly at the Planck scale, then this is an equality. And then if it's larger than the Planck scale, of course, it's an inequality. So what we're considering some quantum field theory that admits a cutoff like that in order to have a finite bound. And that leads to the sphere null energy condition. This is for the minimally coupled scalar in a four-dimensional Minkowski space. So this is a quantum energy inequality with a lot of limitations. Limitations in the field, limitations that are just for Minkowski, and limitation that it includes this UV cutoff in the bound. So it's a very, very limited quantum inequality. So the bound is as I said, is the f prime as required by the rescaling of the affine parameter. And then we have the b here. So the b is a dimensionless parameter that is going to include the physics of our problem. So what is b? So b could be the largest value of b would be 1 over 32 pi, because 1 over 32 pi is exactly what makes this equal. So if the UV cutoff is exactly Planck scale, then the B is of order 1. However, we can be motivated to consider B less than 1. So this inequality is not saturating control construction. So what we mean is if we have some effective field theory, then we can have the UV cutoff far from Planck scale, and then we have an inequality here. The UV cutoff is it's kind of larger, and then the B can be smaller, and the bound can be smaller. It means it allows for less negative energy. So there are like some considerations for what we're taking B to be. So we do need to use the semiclassical Einstein equation in order to connect the renormalized stress tensor with the Ricci tensor. So because in both the theorems we needed a condition that is a condition on the curvature. Now, I'm not claiming, and I won't solve this equation, which is notoriously difficult, and very few solutions have been derived. The only thing I'm doing is I'm assuming that we have a metric and state that form solutions of this equation, and so we're just connecting the quantum object with the classical curvature in a purely semi-classical setting. So with assuming the semiclassical Einstein equation, the Snec condition is exactly translated to a condition on the curvature, which is of the form that we have. And then in our theorem, we also assume the pointwise condition for the reasons I explained before. It's about the boundary conditions of the functions. So due to the boundary condition of the function, we also always need this pointwise condition. And then we have the mean normal curvature of P that has to be smaller than this function that now we know what it depends on. It depends on B, it depends on L0, how long this is violated, and also the L, which is where the formation of the focal point is. So since we've used this condition for quantum field theory, our assumption is also going to depend on that. So let's see how much is this, put in some numbers in a simple model and see what kind of predictions we get. So we have a toy model of evaporating black holes that is the following. So we will assume a Schwarzschild geometry in order to compare the mean normal curvature of spherical symmetric hypersurfaces with the prediction of our theorem. So that's the only thing we do here. So we're comparing some H for a spherical symmetric black hole to what is required. So what do we want to see here? So here in this picture, the outer circle is the Schwarzschild horizon, while the dotted circle is our hypersurface P. And it has to be inside the horizon because we require the H to be less than this negative expression. So it necessarily will be inside the classical horizon. Only if it was zero, a marginally trapped surface, in this case it would be exactly on the classical horizon. So what we want to see is for what values of L this will be how far inside the black hole that would be. So how far inside the black hole it has to be. What we want is for that to be as close to the classical horizon as possible, then that means our theorem is good. If it's very far inside the black hole, it means our theorem is not very good, doesn't have a very good prediction. So we want small x be close to the horizon. And these are some results, and as you see, it heavily depends on the value of Q1 or the value of B. So this Q1 is 1, is exactly the maximum value of B. So yeah, it's this, it's right here. It's in the energy condition. So that is pretty much B, right? So basically what that tells us is if the UV cutoff is in the Planck scale, that's like the worst case, then the smallest the smallest value for nu we can get is 1/3. So we have to be 1/3 of the distance inside the classical horizon. So this is pretty bad. We have to be too far inside. However, if we consider a little larger UV cutoff, so like Q1 0.1, for example, 1 order of magnitude, then we can go much closer to the classical horizon. So as we expected, it heavily depends on the B, so it depends on the value of the UV cutoff. If we have a large UV cutoff, we can be very close to the classical case. If we have the smallest one, we have to be very far inside the classical horizon. All right, the very last thing, I have 3 minutes or so, right? I'm going to talk about the same application for the area theorem. So we use the exact same condition that we already talked about, and we're going to do an estimation of the evaporation rate. So this is the evaporation rate for spherical black holes that has been estimated a long time now. And here the alpha depends on the kind of particles the black hole is emitting. So for large black holes, we take this value 2 times 10 to the -4. It's a dimensionless parameter. And the interesting thing is that that goes as T to the cube, which is the temperature of the black hole. So T Planck is the Planck temperature. So from our theorem, we take L to infinity, which we can take here. We don't really care as the singularity theorems where the singularity is, so we can take L to infinity. We optimize in L0, and we take rho 0 to have a negative value. So this rho 0 comes from actually 2 different sources. It's from numerical calculations of quantum semiclassical black holes, and also this T to the 4th has been predicted by also semiclassical analytic calculation. So it is a well-known result. So we put it as a suggested value for the rho 0, and it's negative. So the NC is violated here. And from the theorem, what we get from the theorem is this expression. So of course it depends on B again, and it has a dependence of T squared. So what's kind of interesting here is that actually at some point these 2 functions are going to meet at some temperature, and we're going to provide, the theorem is going to provide a stricter evaporation bound than the evaporation rate that is predicted. And this is the results. So this line is for the red line, the orange line is for the largest possible value of B. So the B approximately 1, the UV cutoff very close to the Planck scale. And we see that this provides a boundary evaporation rate to a very, very large temperature where we probably cannot really trust our results. However, again, if we consider a smaller value for B, that will be smaller and smaller temperature. So the smallest the value of B, the larger the UV cutoff, the smaller the temperature, our theorem will provide a bound to the evaporation rate. So what we saw today, these are some conclusions, but I wanted to discuss one very last thing for maybe one minute. We do have better null energy conditions. So we do have a better null energy condition than the snake, and it's the double smear null energy condition. So here, instead of integrating over one null direction, which as we said has no lower bound, we integrate over two null directions. So this should have a square here, is over a null area. Right, so we're integrating over this null area in the two null directions, x plus and x minus. This is the same quantity that we had before, and the bound is approximately goes as how much is the support of the test function in these two null directions. So of course it diverges if one of those goes to 0. So this is a nicer bound because we have proved it actually for cases with curvature, only for the free scalar field, but we can have curvature. They have some curvature corrections here, and it also does not depend on any arbitrary cutoff, but only on the smearing in the two null directions. Unfortunately, we don't know how to prove any theorem with this condition, but we have made one step in that direction. And this is in the time-like case. I didn't talk about the time-like case. I'm only going to give that in this last slide, which is a time-like singularity theorem with a world volume bound. So here we considered this kind of quantum inequality, which is integrated over a space-time volume. And for that, we actually proved a time-like bound and proved the linear theorem with in the time-like case. So the hope is maybe we can prove also relativity theorems with a bound like that in the null case. And I don't know, I hope I will have some results on that soon. Thank you.